So the final presentation this afternoon is Professor Paul O'Brien, also without a chaperone, from the University of Leicester, who's going to talk about the STFC Exoplanet Science Review.
Better. Okay, so I shall, as Louise I'm sure felt, it's very hard to follow the act that we saw earlier. This is a review presentation, so it's a bit different to what you just heard. This is not a presentation of lots of science cases. This is a presentation of what our panel thought the UK should be doing in the future in exoplanets. And I had the privilege to chair this panel, but I really felt like the idiot in the room, since I don't work on exoplanets at all. I work on gamma ray bursts and active galaxies. So you might wonder, what am I doing on this panel? But I'm the chair of the Astronomy Advisory Panel to STFC at the moment. So I was asked to chair this as a sort of unbiased, independent referee, if you like. And the experience was very educational. It was very nice to see what was going on, and I certainly learnt a lot. And what I discovered was that this is a very dynamic community. It's a very pushy community, you might say. But it's a great community. I really got a good sense that the UK is doing really well. And I was ably assisted by all my colleagues here, and indeed I'll show work from some of them as we go along. So I just thought I'd say a little bit about exoplanets. Exoplanets is a subject that in a sense didn't even exist when people like me started in astronomy back in the 80s. So in one generation, we've suddenly gone from having not a single planet known, confirmed outside our solar system, to thousands. It's a complete revolution. It's one of the biggest revolutions in astronomy. This is a plot that Don Placker made for me yesterday from the Exoplanet website, which some of these are candidates, that is, they might not be real exoplanets, but just to show you, this is a plot of planetary size in Jupiter radii, so there's the Earth size, against where they are in semi-major axis. So this is where the Earth, so that's where the Earth is. So one of the big changes that's come about is our view of what we mean by a system of planets. And a lot of these objects, as you can see, are very close to their parent stars, 10 times or closer than our Earth is, and yet they're quite big. These are the so-called hot Jupiters up here. So these are thought to be gas and ice giants, and yet they're very close to their parent star. And this is an example of our change in knowledge, or our profound ignorance, if you like, of what are these planets doing there, where do they come from. But more recently, we've managed to push down to find objects that are at least of the right size to potentially be Earths. We don't yet know the mass of most of these objects, as I'll show you, but we're getting there, and at least these objects are now available, and will become more available, objects like that. And one of the goals, of course, of exoplanet research is to find objects that are, if you like, the twin of the Earth. We regularly see press releases, often from the Kepler team, saying, we found Earth's twin. What they mean is they found an object that's the same size as the Earth and might potentially be an Earth-like object, but we don't even know the mass of most of those objects, let alone what they're made out of. We can find objects using a variety of methods. I'm going to talk primarily about the transit method, because that's where the UK has been leading, but also radial velocity measurements, and I'll show you the two main methods in a minute. But you can also do direct imaging. You can actually see exoplanets if they're far enough out from their star, and micro-lensing is another way of doing it. So here's the two main methods. I'm sure a lot of you are familiar with these two. So one is to use Doppler velocity, so just take spectra of stars, and the star, if there's a planet going around it, or a set of planets, the star will appear to move around its center of gravity with the planets, and you can measure the velocity of the star relative to its average velocity, and you'll see it move in and out of the plane of the sky, as it were. So it will come towards you and go away from you, and you'll see blue and red shifts in the spectra, and you can use that to infer planets are present. And that indeed was the way the first planets were found, 51 Pegasi, some years ago. But today, most exoplanets are actually found using a related technique, which is using transits. So this is like doing the transit of Venus in our solar system. You see the planet or the object go across the face of the star, and it literally just blocks out some of the starlight, depending on the size of the area of the object relative to the area of the star. It's, in a sense, that simple. It's much more complicated in practice. These dips are very small, however. Most of these dips are a few percent at most, because of course planets are much smaller than stars, at least most stars. So today, if you want to find a planet, this is the way most planets are found, by transits. But if you want to get the mass of that planet, you then have to go and use this method anyway to do radial velocities. And this is by far the harder one, because it's very hard to measure the velocity accurately enough. And particularly for low mass planets, you need to go down to centimetre per second accuracy almost. So it's very hard to do that with a stable spectrograph. So why was the review called for now? Well, it's because the situation has completely changed from the time there was a last review by Martin Corcoran and his panel, 2007, and I was attracted to this sentence in the executive summary, which was basically saying, get your act together, guys. There was a lack of coherent ambition, strategy, planning and funding. So you might say, well, let's shut down that area then. That didn't quite happen, but what happened between now and then is that the community has got its act together and got funding. So a lot of what has happened has actually not been because of funding directly by space agencies and STFC, but by university groups getting their act together and collaborating and funding things. And I'll show you some examples of that. So we were asked to review the area, consult the community, and it's a panel, as I said, made up of various advisory panels, solar system and astronomy advisory panels, plus some experts. And other than that, we were just left alone to decide what we wanted to do. So we consulted the community. We had various meetings last year. Some of you may have been involved. So we asked for technology, facility white papers. We had meetings where people could say what they thought. We had an online questionnaire, which was very entertaining. People saying what they thought of each other, almost, as well as... This was anonymous, completely anonymous. And in fact, I asked STFC not to tell us who had submitted the comments, because it's not that big a community, but they could guess who some of the comments were, particularly one person who put their name in their comment. And then we presented the draft report at the annual, there's an annual meeting of the community, which is a great idea. Last year was in Warwick. So we presented the draft report there. Unfortunately, I wasn't at that meeting, but it was presented. And then we had a second round of comments over a few weeks, until finally we submitted the report. It's been a bit delayed in being publicised much, and that was because of the election, partly because STFC weren't allowed to do as much as they normally would in that period. But now it's live, and I'll show you the website address in a moment. So here's just a summary of who submitted, and what was great to see was a very wide range of career status was represented, a lot of PhD and PDRA representation, and that's just a reflection of the age of the community. This is quite a young community. There are some more senior staff involved, of course, but there are a lot of young astronomers involved. This is a community that's growing fast and attracting people. It's an extremely broad community in the UK. It represents people who are finding planets, so the techniques in the top quadrant there, people looking at planets directly down here, but also people looking at stars, because of course if you want to understand planet formation, you've got to understand star formation and vice versa. And one of the big changes has been that it's now recognised and accepted that a very large fraction of stars form planets as part of their formation process. So we assume that, of course, it's in all the textbooks, but now we have clear evidence. There's no argument now, it's a very common process. But this shows how broad the interests of the community are. That's both something good and bad. It makes it hard then to fund everything adequately. So the community, which has grown a lot, is soon going to have to decide, in some sense, what its priorities are. And that's part of what we tried to come across with in the report. And then the last statistics plot I'll show you is just publications. So the UK is in the dark blue columns there. The US is, of course, in the lead. But you can see we're now kind of second. We're doing much better from 2007, when the last report was, the community has just grown and is doing very well and is leading in many of the areas. And that's really important. We're not just participating, we're leading many of these areas. So I'll now show you some example science plots. This is one very recently. In fact, it's a paper led by a member of the panel, but it came out after the review. This is showing spectroscopy of various exoplanets. So the points are obviously the data, and the lines are models, and you can see how hard it is to get enough data to constrain the models. And what was happening here was there was an argument about, are exoplanet atmospheres lacking water, which would imply that something went on during the formation process, or is it just clouds and haze in the planetary atmospheres that is blocking the view? And David's team concluded it was the latter. It wasn't that water was being removed during the formation process. But you can see how hard it is, even for the best cases. You'll notice the name of the planets there, and the word WASP appears. That's the Wide Angle Search for Planets. That's the UK university-funded and STFC-supported facility that has found most of the planets around bright stars. And the advantage of that, of course, is that you then have lots of starlight available to do the follow-on characterization. So the Kepler mission in space has found most transiting planets by number, but most of them around stars that are too faint to then follow up. So what you actually need to do is find planets around bright stars. And that's what the UK has been very good at, and that's then led to other things. But we also have lead roles in other areas, and in particular, of course, the UK is always strong in theory and modelling. And that's very important. You need to construct those sorts of models. And so here's an example just of work done using the Dirac facility. This is the UK's high performance computing national facility, a set of nodes around the country, like at Durham, Leicester, for instance. And this is an example of really detailed work on how you form planets around stars, putting in magnetic fields, all sorts of accretion processes and so on. Really difficult stuff. Now, where are we going next? Well, this is an interesting time because the UK is just right now commissioning a new facility to follow on from the WASP facility. It's called NGTS, which literally stands for the Next Generation Transit Survey. I'll show you some more slides on that in a moment. That's a nice image of it. You can see it here. It's actually on Paranal in Chile. So this is going to be the premier ground-based facility for finding transiting exoplanets over the next 3-4 years. And that's going to lead up to the launch of a space mission, a large space mission. There are others that are smaller, but the large space mission is the Plato mission. This is the ESA M4 mission. This is going to L2. That should be M3 actually, mission going to L2. This is all those objects here are telescopes, individual telescopes. So it's like putting this into space. And because you then don't have the atmosphere at all, of course, you can get much better precision and really get much better data. So here's an example. This is what NGTS looks like with astronomers for scale. This is a plot provided to me by Pete Wheatley, the guy in the blue shirt there. You can see the VLT up on the mountain on the top there. And these are 12 modest-sized telescopes. You don't need giant telescopes to find exoplanets. It's often something contradictory, but you need a telescope that's a few tens of centimetres. It's more than big enough if you do it right. So here are 12 telescopes, and the reason there are 12, not just one big one, is having 12, you can then point in different directions, cover more sky area, find more planets. So this is being done at the moment, and this is really why it's being done. This is a plot showing, again, the size against the star radius now. This is a plot that Pete Wheatley provided to me. This is showing all the candidates. And you might say, well, WASP in green there isn't doing very well. It's only got a few green points. What about all the blue points? But if you ask a different question, if you ask how many of these objects have a mass, well determined, you get this plot. So WASP dominates this. So this is the UK discovered planets dominating in terms of objects that have masses determined to 10%. And that's back to that point I made earlier about you need bright stars. And this is the 20% number. It doesn't really change very much. NGTS will fill in that part of the diagram. So NGTS is going to allow to push down to objects getting towards the Earth certainly Neptune-sized objects, not just the hot Jupiters, and really helping us to understand the true masses and hence get information on the internal structures, the densities and the structures of exoplanets. So here's NGTS in action. You can see the VLT laser guide star system having a great time at the back there. That's kind of a pollution to NGTS. It's a problem for a lot of astronomy these days. You can see the telescopes are moving around a bit, but just to show you the difference, there's an exoplanet light curve, a transiting light curve of a particular planet found with WASP 4b. These are co-added data, adding together data from lots and lots of transits. Here's the same object from NGTS with a single pass. You can see how much, much better the data are. Fantastically accurate photometry. And I should say these data were not taken from the world's premier observing site. These data were taken during a test from the roof of the observatory in Geneva, which is not one of the world's best observing sites. But you can still get to millimag, thousandths of a magnitude photometry. And you can do that because in the images you have thousands of stars and can use them to sort of zero out the atmospheric fluctuations. You can just divide by the data itself and drive down your errors. And also they're paying much more attention now to the calibration of detectors, the accuracy of pointing and so on. And the pixels are smaller. So this is really going to be the revolution that's going to drive our program. So the review panel, come to our conclusions, made 17 recommendations, and I'll bore you with all 17 in a moment. But these are the 4 aims, really. What do we want to do? Well, the prime thing we thought we should do as a country is trying to zero in a bit. So although we'd like to support everything, if push comes to shove on funding, we have to decide what our priorities are. So the first aim was to support the transit roadmap. That's that roadmap from NGTS to Plato. So the next decade, so we assume towards the end of the next 10 years there'll be another review, but over the next decade we should support that roadmap to make sure that the UK can exploit the facilities it's investing in. We need to understand atmospheres. So once you've found your planet, you look to see if you can see an atmospheric characterization signal from the exoplanet. That's the really tough bit, the data that I showed you earlier. And to do that, of course, you need access to spectroscopy instruments, and preferably niche, carefully designed instruments. We want to understand how to form planets, of course, so that's star formation again. And of course, we want to do the statistics, and also looking around cooler stars, smaller stars, where you can actually do some really interesting work. And indeed, you can do work on things that are dead stars. So our president, of course, who works on white dwarfs, you can look at the pollution of white dwarf atmospheres, for example. So that's where the star has eaten planets. These are accreted objects, and those objects will pollute the chemical signature of the white dwarf. Things like that, which wasn't even thought about 10 years ago. So what are our 17 recommendations? I'll quickly go through them. Obviously, support science, support high-performance computing. With my sort of astronomy advisory panel hat on, that's one of the big messages from the UK astronomy community. We can't just take observations, we need to support theory. And we have arguably the most successful system in the world for providing high-performance computing, the Dirac system, and the government even is impressed with Dirac. BIS thinks this is a fantastic example of how to do it and is providing millions of pounds of additional funding on top of STFC's budget to provide this facility. Dirac 3, third version, is hopefully coming along. Fund the transit roadmap, of course, but we also need to do the radial velocity measurements. We need to get the mass of the system. And one of the clear messages from the community was these facilities should be available to everybody, not just to a small consortium of people who may have thought it up. That's a rather contentious point because sometimes little consortia get money, but in the north, there's a facility being reviewed right now by STFC, came after our review, called THE, and that will probably go on the INT, on the Palmer, and turn the INT into a radial velocity machine. And that would be fantastic for the community in the north. And of course, support Plato. So we want to do planetary atmospheres, so we want to support exploitation, we want to build instruments to find exoplanets and characterize them. And of course, in the future, we're part of ESO, and we want to have instruments on the ELT, the Extremely Large Telescope, the 40-metre class, to study planets. And of course, ELT is next to VLT. It's on an adjacent mountain, and NGTS is right there. So it will naturally provide things that ELT can look at. Every planet that's found with NGTS can be looked at with ELT. And then the last two were just studying the structure of disks. Every telescope you care to name, we need to support the theoretical interpretation of that. We need to look at the statistics. So another way to find exoplanets is to use microlensing. So transits is where you see the light drop as the planet goes in front of the star. But if you have the configuration just right, the geometry just right, as the planet or even a moon goes in front of the star, you can boost the light from the star through gravitational microlensing. Some planets have been found that way, very few now, but some missions which are not, as it were, built to do this, but can do it, like Euclid, which is a cosmology mission. There's a proposal to do a microlensing survey on Euclid, monitor lots of stars, and see these very rare but very important changes. And they're important for one reason, that you can see low mass objects, small objects that way, which are hard to do using transits. And likewise with Gaia, you can also see objects, and you can even do astrometry. You can see the wobble of stars in the plane of the sky. So there's radial velocities in and out of the plane of the sky. So there's lots of ways to find planets, and so whether we have enough money in the system to do all of this is TBD, but there is potential there for the UK to lead on lots of these things. And then lastly, we had recommendations on technology. Of course, this is looking sort of longer term, beyond the next 10 years, developing blue skies technology so we can take a leading role in the next generation of instruments on the ground and in space. In particular, there's, for example, a mission under consideration right now, a mission called Ariel for the M4 slot, the ESA M4 slot that would launch way through the middle of the next decade, but that would be an example of a space-based spectroscopy development mission. So if we can do all that, we can then populate our exoplanet facility timeline, not just with things like WASP and NGTS and Plato, but all the other telescopes. So either you use facilities that are general purpose, so things like ELT, and of course JWST launching in a few years, but you also build niche machines. These are two small missions that are going to launch soon to find and characterize planets, and then way off into the future. So the UK has a very strong community, very ambitious community, and of course one day someone will be standing here showing you, perhaps not an image as good as that, but something where they can say, yes, there is an ocean on that world, it's raining on that world, just like being here. It's a really damp, dingy place. Obviously, UK astronomers should be leading this kind of work, right? Finding this sort of world, but it will be true. And it's extraordinary to think that we are on the precipice of finding such objects for real. It's a really exciting time, so thank you very much.
So we have a few minutes for questions if there are any. Steve.
So I think that looks like a very exciting report in what is, in my view, an extremely exciting field. Did you have a look at all at supporting the individual scientists and scientific groups? And I'm thinking in particular of making use of the European Research Council, where I know on your panel both Giovanna and David have got ERC fellowships, and whether there's anything that can be done to support UK applications to the ERC a bit more from the community as a whole.
It's an interesting idea, assuming we stay in the EU, of course. It's a general problem, and certainly, Steve, at our institution, getting the manpower available to help you write the proposal, as you know, it's a lot of work to write those proposals. And there's a kind of art to it, in a sense. You've got to know the jargon for the EU bureaucrats. But likewise in this country, writing fellowship proposals and so on. Now, the community, in a sense, this is true across astronomy, should be supporting itself. in some sense. People should be saying, well, I've just got one, I'll help you get one, because you're then not in competition anymore. What some people said we should be doing is perhaps targeting some funding to particular science areas. So saying, well, we're going to do exoplanets, so let's carve out some fraction of the budget. I was opposed to that, and I think most people are opposed to that. I think we should stick to the fund the best science argument. But the community is doing all right. I didn't show the plot of the fraction of funding in the UK that's going to the community, but it is relatively doing okay, I think.
Robin?
Paul, congratulations on a good review, very worthwhile. Congratulations on a good review. The large range of areas covered, unless the community is huge, suggests to me a large number of very small research groups around the country, and I just wondered if the panel had looked at that at all, especially in terms of development and coordination of the UK effort, instrument building and so on.
Yeah, I mean, that's why we think there should be some focus. The community's had a period of kind of exponential growth, as it were, and that can't be sustained in the current, well, any funding climate, really. So the community is going to have to decide. Of course, there is room for individuals to do some theoretical work, say, or join an overseas observing team. We can't fund everything. So in terms of funding facilities to find planets, for example, the transit method we favoured over, say, direct imaging. Some people might want to put a lot of money to build an instrument to do that. We said no, we should prioritise the former. So there is some change that's going to have to come to the community, but we didn't think that was for us to really start ordering academics as to what research you should be doing. Rather, we were giving advice to the research councils and saying, this is what we think the primary science goal should be to support that transit roadmap.
One here. From Fred, and then I think there's one further back.
I'm Paul Daniels. I'm the president of the Guildford Astronomical Society, and I can confirm that it is possible to detect exoplanet transits with small instruments, because we've detected 2 or 3 exoplanet transits with a modest instrument. Now, is there anything in your roadmap to coordinate amateurs to help you with some of the transits on brighter stars?
I think there is a role, this is an area where there is a role for the coordination, and in particular one of the things that is hard to do is confirm those candidates. So you find lots of candidates, and then what do you do? And telescopes which are slightly bigger than the Discovery telescopes, so telescopes are sort of ½ metre size, 1 metre size, which some amateur astronomers even have, or astronomers are ideal for that. So I think there certainly is a role, which I believe the transit community does publish its candidate list, so you could follow up that way and confirm them, and then those are targets for the really big telescopes, because you don't want to give the really big telescope 100 possible things, maybe 5 or 10. So that step between the candidates and the detailed work, that step needs the sort of smallish sized telescopes, which certainly there would be a role for the community in.
Yes. So I was always also thinking you could do follow-up work with the timing of transits.
You could do the
You
timing.
could detect them and perfect.
They don't normally publish candidates unless they've seen several transits, because of course the star itself could vary. So that candidate list is very large, and there's been some recent work that suggests the Kepler transit list, for instance, might be polluted by 40% false positives. Now, it may be 20%, but it's several tens of %. And you've got to filter that down, otherwise you're just wasting very large telescope time.
So there's Fred was the next.
I didn't want to get halfway through the question and have the microphone. Thank you. You mentioned orphan planets, but I didn't quite catch how you define what those are or what you think you can do with them. They were on your top level
I'm not
list.
the expert, of course, but there are orphan planets in the sense there are planets that appear to be adrift, just like orphan brown dwarfs.
Can you detect those?
You can, in principle, detect objects that are small, but it's very hard, of course, to detect an object that's not producing much light itself. So it's certainly not a big area of astronomy. I'm not an expert enough in that to answer your question fully. Where you draw the line, of course, between planets and brown dwarfs is one area. So if you take that plot I showed at the start from the website, I made a plot myself the other day which had thousands of objects, up to thousands of Jupiter size, and I thought, well, that can't be right. And I asked my exoplanet colleagues, and they said, no, anything bigger than about 2 Jupiters is probably either not real or it's not a planet. But of course, where you draw that line is an interesting question, because there are studies of brown dwarfs, like Martin will know. One of his postdocs is working on irradiated brown dwarf atmospheres. Is one way you can study atmospheres that look like planet atmospheres. So there's a role to be found for things that you might not immediately think of are related to exoplanets.
Louise? We're probably just going to have time for one more after that.
Okay. I was just wondering, was there any discussion in looking at the impact of stellar flares or stellar coronal mass ejections on the exoplanets?
You mean extinction and all that sort of stuff?
Just the impact on whether you can sustain life there through the radiation levels?
Yeah, there has been thought. I mean, there is work going on, for instance, in the radio to try and look at that sort of thing, magnetic magnetospheric effects. I can't say it's a big area in the UK at the moment, but yes, the impacts, the number of stellar flares, of course, isn't a completely well-determined number in general.
Yeah.
But yes, there is certainly those very close-in objects, because they may mostly be gas giants, but if they're close-in rocky terrestrial type objects, then it's quite a hostile environment if you have a magnetospherically active star.
We've been trying to work out ways through studying solar flares and CMEs to see whether we can detect stellar coronal mass ejections as well, which may be useful input, I don't.
So we've got one more question. In the spirit of what we're celebrating today, I'm going to let Jane have the last word. No, I wouldn't.
Given how hard it was to get STFC to back transit work a decade ago, and now transit works, woohoo, in the big report, do you think we're backing the wrong horse again? Should we go for a better horse?
Well, one of the reasons NGTS is being backed, of course, is the hardware has been paid for by universities. So it's a challenge for the agencies now that a lot of universities, although we're not that rich, if you have enough universities putting in a few $100K each, you can do something quite significant on the ground. So the NGTS hardware is being paid for by university groups. A few 300, so Leicester's put in 300K, for instance. And then STFC are bombarded then with requests for operational money. So it's a challenge for agencies. What do you do then? Because you kind of been blindsided by this group coming up and saying, well, you've now got to give us some money because we've spent our money. That's, I think, the real challenge for agencies. You don't want to deflect them from what they want to, what the community wants to do. What was reassuring in this report was the community backed NGTS. So most institutes are not involved directly, but they backed the exploitation of NGTS, and that's because NGTS is exactly the facility you should have built to find planetary and bright stars.
Okay, well, sadly we have to draw things to a close because, as you probably know, we have to finish early this afternoon.